let's summarize what we've learned so far. We know that we cannot return a reference to an owned parameter or a reference to an owned piece of data created within a function body, because either scenario would create a dangling reference. The lifetime of the returned reference would exceed or outlive the lifetime of the referent, the original source of data. Our goal in this lesson will be to return a reference from a function and understand the only technical situation in which that act is possible. So let's take it step by step. We'll begin by defining a function called select first two elements. And this function is going to extract a slice from, say, a vector and then output the elements. So for now, let's not even worry about return values. We're just going to take a slice of the first two elements of a vector and print it. So I'll define an items parameter, and I'll set this to be a vector of strings. No return value yet. And in the body, I can declare a selected items variable, and I will create a slice. So a slice is still a reference. It's a borrow, but of a fragment or a portion of the collection type. So I'll provide my borrow operator and then my items vector. And then to get the first two elements, we can either do 0 dot dot 2 or remove the 0 because that will start from the beginning anyway. And now we have a slice or a reference to the first two elements of the vector collection that is passed in. And below, I can print line and use debug formatting to output selected items like so. So now we can invoke this function in main. Let's define a vector called cities, and we'll populate it with 3 cities, and they have to be strings. So let's do a city of London, and then let's do a city of New York, and finally, let's do Barcelona. And that should do it. So now I can invoke select first two elements, and the function expects a vector, and it's going to take ownership over the vector. So we're not even dealing with references yet, but we can pass in cities. That will move ownership to the items parameter, so we will not be able to use cities afterwards in main, but for now that's totally fine. You can see we're going to output the first two elements. Now, if we want to improve this design so that we don't lose ownership, the obvious refactor is to convert items from being an owner of the vector to receiving a reference to a vector of strings. And that will allow us to not lose cities in main. That's going to be a very simple change. I can simply provide my ampersand right here to indicate that items is now a reference. It's a borrow of some vector of strings. And then all I need to do in main is to update the syntax here to pass in a reference. That will be an inline reference created on line 12, and it will be gone as soon as the function is done running. And this code will execute the exact same way. We can improve the type of the items parameter to be even more flexible. So we can change to this syntax. We can say we're going to have a reference to a slice of some collection of strings. And the syntax looks like this. We're just going to declare a pair of square brackets and then string inside here. This is still a reference. In fact, it is a slice, just like we have here, a slice to some collection of strings. We are not hard-coding the specific collection type, such as a vector. So the advantage to this type is that we can pass in a more dynamic collection. We can still pass in a reference to a vector of strings, or we can also pass in a reference to an array of strings. Either one will work because Rust will use deref coercion to coerce either type to this expected type of some slice, some fragment of some collection of strings. So for example, in the body of main, I'm going to declare a coffees array. So I'm just going to provide square brackets here instead of the vec macro. And in here, I'll declare 2 coffees. Let's do something like latte, and then let's do mocha. And then similarly, I can invoke select first two elements, and I need to pass in a reference. A slice is a type of reference, and I'll pass in a reference to my coffees array, and the code will work as expected. Now let's make the code even more interesting. What I'm going to do is take the second example and move it into a block within the main function. And that's just to show you that cities and coffees are now going to have different lifetimes. The lifetime of cities is the body of the main function, and the lifetime of coffees is only for this nested block. Now, in either one of these examples, due to non-lexical lifetime scopes for references, the reference that we're borrowing only exists in one line, but the reference is always connected to the referent, the original source of data, and now we have a different lifetime for each respective referent. Cities has a longer lifetime or a different lifetime from that of the coffees array. So every time the select first two elements function executes, it receives a reference to some data that lives outside of the function, right? The data is declared within main and lives in main. That means that the lifetime of this reference that is being passed in is dependent on somewhere else, some other region of code where the original referent and the reference was declared. This function is oblivious to what's going on in main. Main has two examples of referents that have different lifetimes, and yet this function is gracefully able to handle a reference to either, despite the fact that the referents and the references have different lifetimes. Now, in this example, the borrow checker does not have to worry because it does not have to track the lifetime of the item's parameter after the select first two elements function ends. There is no return value, so there is no risk of returning a dangling reference. We're just going to receive a reference and do something with it, but we're not going to preserve it through a return value. Thus, Rust can guarantee that there's going to be no dangling reference, and it compiles just fine. Next, let's consider the scenario that this function returns a reference parameter as its return value. Let's say, in fact, that it's going to return this slice. This is going to be totally valid, but it does introduce some complexity because the lifetime of the original referent that items will be based from exists outside of the scope of this function. This function is going to act like an intermediate step. A reference is going to pass through this function. It's going to enter as a parameter. Then we're going to use that reference as the basis of creating a slice, its own separate reference, that we're also going to want to return. So it's going to be critical that selected items is connected to the original referent from which items is coming from, because the two are going to be intrinsically connected, right? Whatever is the source of data that items is borrowing from, the selected item's lifetime must live within that referent's lifetime in order to prevent selected items from being a dangling reference, right? The original source of data from which we're going to target a fragment of the first two elements must live as long as selected items does, so that selected items, that slice, never becomes a dangling reference when it is returned. So let's update the function to return our slice. It's going to be very similar syntax right here. I'm going to provide my arrow and then ampersand and then some slice of strings. And now I'm going to get rid of my print, and I no longer need a variable either. I'm just going to take a slice of the first two elements and get rid of my semicolon. And so now I am returning a reference, right? And this is going to work. So notice that we are passing in a reference and we are returning a reference, and that is fine with Rust. Behind the scenes, the borrow checker is inferring that the lifetime of this return value is connected to the lifetime of the item's parameter. In fact, this is the only valid way that a reference can be the return value, and that is that it is coming from a reference parameter in some capacity. That is the only technical way given the constraints that we've seen from the previous lesson. Any piece of data created here or any owned parameter will go out of scope, so we cannot return a reference to that. So the only way that we can return a reference from a function is if it comes from some parameter, and that intrinsically means that this returned reference must live within the lifetime that the original items reference lives within, or that reference of items, its lifetime is directly connected to this one. It's very similar. They must both live within the lifetime of the original source of data. So let me show you right here that I will assign this return reference to a variable. Let's call it 2 cities. And similarly down below, I can assign this to 2 coffees. And I can output both of these slices. So 2 cities in debug formatting, and below we'll do 2 coffees in debug formatting. All right, I want to show you that this example is going to work. So the key takeaway here is that 2 cities is a reference fundamentally to the first 2 elements of the city's vector. The city's vector's lifetime must be long enough so that 2 cities lives completely within it. Because if 2 cities and its lifetime expands past the existence of the city's vector, then we have a problem. We have a dangling reference. So for example, if I try to, let's say, drop cities right here, we're going to get a compiler error because Rust understands that the lifetime of the 2 cities reference is intrinsically connected to the lifetime of its referent of the city's vector. And thus, if we get rid of cities right here and deallocate it, 2 cities will be a dangling reference. We talked about the exact same example a few lessons ago, but here's the kind of new takeaway. How was Rust able to understand the association that 2 cities had with our original source of data, the referent? That is because when we passed in this reference to cities right here and it became items, Rust inferred or assumed that this return reference was related to the lifetime of items. That whatever is returned here is a reference that will live within the lifetime of the referent. And how did Rust know what the referent was? It was wherever items got its reference from. So since items, the reference, got its reference from cities, and Rust assumed through logic that we'll talk about in the next lesson, that the return value is also related to that referent, Rust understands that 2 cities must live within the lifetime of cities in order to avoid being a dangling reference, and thus it knows this code will not compile. All right, it's really all there is to cover in this lesson, so I'm going to get rid of this code and run it one more time to show you everything is functional. Key takeaway, we are able to return a reference as a return value, but the only way that is technically possible in avoiding a dangling reference is if that return reference is related to some parameter that is also a reference. In this example, Rust is inferring that since we have only one reference parameter, the only logical way that this would work is that the return reference is related somehow to the items parameter. More specifically, that the lifetime of items, or the referent from which it's getting its lifetime from that it's connected to, is going to apply similarly to the returned reference. The lifetime of the original source of data, whether it be cities or whether it be coffees, must live long enough such that the slice to the first 2 elements, the slice to a fragment or a portion of the first 2 elements, that is still a slice that is a reference. It can only live as long as the original source of data, and as this reference passes through this function, Rust understands that through some inference, and thus it's going to be able to validate that 2 cities remains a valid reference throughout its whole existence. So again, when we're dealing with concrete lifetimes in a single function body, it's a lot easier to visually see the regions of code. Now we're talking about passing references to and from a function. That is where the complexity sneaks in, and the borrow checker is trying its hardest to validate that there will be no dangling references. There's going to be no opportunity for a piece of data to go out of scope or be deallocated and have some reference still present in the code. That would create the potential for bugs, and the borrow checker has to enforce the same standards, but now living across references being passed into and out of functions. Hopefully the benefits here make sense and what the compiler is trying to do makes sense. And we're going to practice a lot more with these examples with more comprehensive explanations in follow-up lessons, because I know this kind of topic can be confusing at first glance. With that, I will see you in the next lesson.